Perfect. Well, thanks very much, everyone, for coming to the talk. It's been really interesting so far just to understand people's different perspectives on all the different work. And I come from perhaps a more classic, I guess, space problem. So the things around debris, the things around numbers of objects, and what impacts it may have to operators and future ways in which we deal with our spacecraft. So I don't work in isolation on any of this. I still work with my team in the onboard data handling research group, as well as the staff that we have here that work in the ground station, which is where I am today. The background that obviously we've heard from Dr. Mamata already is around the increased number of objects and the increased problem that we have around debris as well. And of course, more objects means more conjunctions, and conjunctions are ways in which we describe how two different objects intersect with each other. So usually it's a 5 kilometers kind of ellipsoid around each of these objects. And when we can look at this 5 kilometers sort of thing, we can see just over time that the number of objects as they increase, unsurprisingly, the number of conjunctions are. And what I've been investigating and I want to talk to you all about today is how we might want to cooperate better so that we can get more real data back down to the ground. And the problems really that I'm sort of finding and have had to face in other projects, not just with this, but we're perhaps with working with NORAD, JSPOC, or with ESA, is that how cooperative we can really be on these topics when actually they can be quite sensitive to the way in which an operator works. So you may be really cooperative within your own organization or within your own constellation, but otherwise, why do they need to tell you anything? And unfortunately, there's no rule, there's no regulation that really is stopping them from going, no, we don't need to do that. And of course, that may change, of course, with the Space Industries Bill. And we need to kind of understand what those future limits and questions need to look like so that if we are launching these things, what regulations should they follow? What will the future look like under these circumstances if we allow certain behaviors to continue? So that's really what I wanted to talk to you about today. And we can kind of see here, of course, when you've got more debris, collisions, whether it be from ASAT tests or otherwise, then these number of objects is going up massively. So when it comes to the data itself, there's kind of 3 areas we can talk about. One, precision and accuracy, i.e. when you get some data of a satellite's position in its orbit, whether it be relative to something else, such as in the data you would get from a conjunction data message that comes down via JSPOC and NORAD, whether it be something that's standardized, so as in that everyone knows how to deal with a GNSS or GPS signal, the fact that it's in a WGS84 frame, how much standardization has gone to that, and importantly, how much do they actually share? So we've kind of got 3 big areas here. One, two-line elements, which I'll talk about in a bit, are ways in which then NORAD gives out data on what satellite positions actually are. They are very standardized, they are shared all the time, they are not very accurate. And TLEs have a certain level of precision, and that will soon be superseded by a new format that is coming out as well. But the precision and accuracy behind those tools, we don't know about because you don't have access to the real data or understand what the bias is introduced to these systems. With something like GPS as well, it's highly accurate. We can get meter level accuracy on what our satellites are actually doing. They're very standardized. But who is actually sharing this data? And there are some really good operators that do share ephemeris data, which is derived from GNSS or GPS measurements. But not many people share this, mainly because, 1, they don't have to, and 2, it actually might then expose themselves to the ways in which they operate, and importantly, the risks with which they're willing to take. And if you can kind of reverse engineer decision making on conjunctions, well, that could affect someone's liability, their insurance, and maybe there are these operators that just, they don't move, or they don't want to, or they dismiss these perceived risks of when they come up. And other systems that exist are ones such as envision systems. So whether it's telescopes looking up at the sky between dawn and dusk, Doppler and ranging sort of RF measurement systems, these are all can have highly accurate, they can be quite standardized again, but they are shared perhaps a bit more. What we've found is that satellites used to have Doppler and RF measurement systems 20 plus years ago, and there was a whole issue around over-reliance on NORAD for giving out this sort of data, and that's kind of just disappeared. People are just taking it as gospel, and yet all of a sudden, if someone really wanted to turn around and launch actual military rockets that weren't we used for even nuclear purposes or for attack purposes, NORAD will just not be looking at the sky anymore. Okay, it wasn't what it was designed for. NORAD was there to be an early warning system for missile defense. The same thing in the UK for our falling down system. At the moment, yes, we are using it for space situational awareness, but it's not what its main priority is, and that can get switched on and off at a moment's notice. And of course, people have not woken up to those possibilities as much, and there's an over-reliance, kind of in my opinion, on these systems. And so the reality is that we have these two-line elements. It's the only data sets that you can really get out on there without pulling your teeth out by working with data providers and license agreements on anonymized data sets to actually get data out. And these are kind of the sort of types of data you can get, really. Some of them can be raw measurements, such as actual like radar measurements, and you can actually get the derived signals based off of a radar measurement. And that would be great. It means it's a real observation, and you'll hear me talk about observation a lot in this talk. And that gets essentially used then by NORAD, by JSPOC, to then interpret that with a certain positional uncertainty. And of course, we're limited somewhat by the TLE line set. So there's only a certain amount of precisions you might have, for instance, on the mean motion or the inclination or any of the other terms that we would use in our spacecraft tracks. But it's interpreted data. Okay, they released it in a post-processed way, and we don't know what manipulations or processes that they've gone through. There are documents out there that tell you how it is used, but you don't know the ins and outs behind it. And essentially, I would just assume that there's a mask of uncertainty on anything that kind of comes out of NORAD. Now, the other thing that people do a lot of is when you see people that look at ASAT tests or are looking at what's happening in the future, of course, we're talking then about orbit propagation. And there's kind of two big types that we have here. One, which is the classic SGP4, and then you have high precision orbital propagators. So an SGP4 is a empirical model that is used behind to then give you then where a satellite's position is ahead of time. The problem is that the positional uncertainty increases further out you go, whether it be in orbits or days, and that really it is useless. I mean, 5 days, is no point you doing a simulation beyond that time. With a high precision system, it may then want to then include more terms around what is in the orbit propagator itself. So that might include J terms or J terms up to 44, the geopotentials, not just with our planets, but of our own geoid, the solar radiation pressure, the drag environment, any of the forces, the attitude, any of that involved, such that you can then get your prediction to be better for longer. Okay, but these then all come with a shelf life. They all have positional uncertainty. And the question is, well, what do we actually want from this? So if we look then at the history of all two-line elements, okay, if you were to write a very unique and powerful Python script, which, say, for instance, could download every single one of them, then what you could do is you can then look at, for instance, the average age between two-line elements for a given satellite. And now the age could be then something that is used to tell you when then a NORAD has decided the one that they've given out is not good enough. Okay, and so they have a number of tracked objects where we can see that the actual age of a two-line element we measure in sub-days. Okay, so this is really good. It means these objects are tracked really well, and that you often get multiple sort of updates in a day. which is really, really good. It's what you want to see. You want to see that there are observations happening, such then that you can then rely that the initial conditions that you're probably going to give to a propagator are actually worth you using. The problem is that there are a whole set of objects that really aren't tracked anymore, that are still in our databases. And when you include those ones that are objects that have not yet decayed and yet are somehow not tracked, i.e. the TLA ages are quite high, well then actually you get some silly numbers from this. And the problem is that the non-tracked objects it's about 50-50. Okay, we track 50% of our objects really, really well because probably those are the ones that are alive or those are the ones that are important. Problem is that all of a sudden there is then ones here where TLEs now are out of date by hundreds of days. Okay, so this is not good. Okay, the fact that then observations now are just not taking place on a certain number of objects. If we were to just look at what happened since 2010, okay, forget going back all the way to the the 60s with when we sort of started pulling the data through, you can then actually see then the average age, and you can see what happens when you have collisions and when a lot of collisions don't happen. But really, the lost objects, the objects that aren't decayed, that aren't being tracked, they're just going up and up and up. And the real problem for that is obviously because we're now tracking more and more objects that actually have more use. We're launching more things that are active, that we do need to track more, that are perhaps in highly populated orbits like Starlink's is, allowing us then mean that all the ones that we don't track have now got less time. So if you're operating these sort of new mega constellations that are coming out, well then these mega constellations themselves, they're growing and growing. So all these other objects, they're just not getting tracked. Okay, and so this is kind of a big worry, certainly to me. And we might want to think about how do we do that? We need to get all of them under control. Okay, because these percentages between tracked and untracked are going to change. But we don't want to have loose objects there that we just haven't tracked for 130 days, because 130 days times, a 1 to 3 kilometer error per day, is hundreds of kilometers. So you have no idea where they are really. And how does this then translate then into conjunctions? And conjunctions is this 5 kilometer ellipsoid that we were talking about. Well, unsurprisingly, they're going up, the number of objects going up. For the well-tracked objects, they're hitting around 50-ish a day, conjunctions of ones where these ellipsoids intersect with each other. But as soon as you add all the lost objects, the untracked ones, then we measure these in thousands. Okay, but we don't track them enough, so the data is perhaps not well understood between these objects. So are these real conjunctions or are they not real conjunctions? And who is tracking that? And because at some point, each of these objects was associated to a nationality and a nation that was launching and owns the risk and the management around some of these objects. Okay, so where does this data, when we analyze this ourselves, one of the people that I talk to a lot around the problems of conjunctions, regulatory processes, and how we should perform measurements is with Professor Hugh Lewis down at Southampton. And he often tweets around what is happening with his Socrates tools and working closely with the IEDC and UKSA. And you can quickly see that, with Starlinks here, you can see conjunctions within 1 kilometer, not even 5, just within 1 kilometer. They're measuring them, per week in the thousands. Okay, so this is something we have to be careful of and worry about. When you see these mega constellations going up, you're going to then all of a sudden going to have a really populated area. They're all going to conjunct perhaps with each other. And so who owns that risk? And importantly, at what point should an operator tell then the taxpayer or the regulatory bodies who they should be talking to with on these issues, whether or not there's a problem or not? Because when I look at this and I think this is just a roll of the dice, each of these times it's a roll of the dice. Even if the probabilities we measure in, sub, 10 to the minus 5, levels of probabilities, we don't want to be doing this when you start measuring those in the thousands. This is not a good situation to kind of be in. So Starlink's roughly is estimated to be around 12,000 satellites when it's done. And these are the other ones. Okay, you can go back, have a look at these different things. And the website that I tend to look at are the FCC, and the FCC are in the States, which do a lot of launch agreements and licensing, together with the ITU, the International Telecommunications Union, for new mega constellations. And you can kind of see some of the numbers here. There's a total number of satellites just on these ones, and these are just the credible ones. This actual list that we have from a spreadsheet is another hideous number. This is 24,000 extra sort of objects here, and I've seen sort of ITU and FCC licenses where they're going, can we have 115,000 objects, please? You know, so these requests are getting big. The question is are they out of control? And the problem is where does that regulatory boundary kind of actually start and stop? So now that we've kind of looked at what mega constellations are doing, the fact that there's lots more conjunctions, how do we solve this problem? And I want to come back to the idea on what is an observation. So an observation is a measurement. It's a measurement done with an instrument that may be done in the sky, it could be done on the ground, but it gives you a level of certainty of when something was and where. And so you might be tracking, for instance, X, Y, Z components in Cartesian coordinates of a particular satellite. And whenever you get an observation, it will come with perhaps a level of uncertainty. So if it was a GPS measurement, we measure that in meters, that's great. But over time, things, can grow. The variance can grow, or the uncertainty of actually where you are grows. And this is a problem because if you remember, we were looking at observation measurements or intervals between observations that we measure in days, okay, or in sometimes maybe tens, if not hundreds of days. So, this variance kind of blows out in kind of an exponential function very, very quickly. And we kind of want to make sure that we have the appropriate observation for what we want our risk situation to look like. And of course, when you start then adding variance to a system, okay, this is when, if you were looking at then the age of just the tracked objects here, when you start to look at then adding the variance, the standard deviation or the 1 sigma of a system, you can start to see then actually what the error is. And then you can convert, the days into kilometers, based on the type of orbit simulation or assumptions that you have to make. So if everything has kind of got the TLH is really good, plus or minus X number of kilometers, well, is that good enough? Because what we really want to have is we want to have more data. Oh, I spelled NORAD wrong. Damn, I'll fix that in a second. And so we want to have raw radar data available. We want to have NORAD data be able to be used in lots of other systems and can convert to other systems. Can we augment that with GNSS or GPS or ranging systems? And can we then perhaps use optical systems where we can to then go, actually, we need more measurements on this because these are critical objects or we haven't looked at it in enough time. And so the questions that we can ask students and ourselves of when we're then looking to build new missions or to regulate or to set policy or within a company or even within a government is, what do we want that future observation to look like? What do you want that variance to look like? Because these are decisions that kind of then can tell you, well, okay, this is the amount of observation you need to meet that. And importantly, how does that translate then to risk? Because at some point, if we're going to be launching lots of, for instance, OneWeb satellites that are launching with a UK flag on them, well, then we need to be able to track them properly. We need to know where they are within certain bounds, but we also need to do that with our partners as well. And the risk could be is that you might know your one object really, really well, but if this other object is really poorly defined, well, just in statistics term, a good number multiplied by a rubbish number is a rubbish number. Okay, so we need to then think about how we do this holistically across boundaries, across borders, and to allow then operators to operate with better behaviors perhaps, but maybe we need to do that with our own local instruments or our own government data sharing policies too. So I've been interested in what does this look like and how we might do it. So one of the things that I go to first is when I look at a ranging system. If it's an RF ranging system, we would send something up from an antenna. We would measure what we call the time of flight and measure it coming back? Well, it really does depend on a number of variables that have a trade space. The first one is this B term here, this beta term, which is our bandwidth. And so essentially, the more bandwidth you can give to a signal, the more precise the measurement you can do. The signal to noise ratio, so how much power you use. So if it's quite a noise-free signal, then you're using a high amount of bandwidth through, well then actually you can then get a better and more sensitive estimation. And the last term there, which is behind this weird strange window, which is N, is the number of measurements that you use to take a measurement. So what I've got here on the plot on the left is what happens for different types of scenarios that you might, for instance, want. You could take a 1 gigahertz channel and take 1 samples of that, and you can get really good accuracies in signal to noise. So if your signal to noise was even 0 dB, i.e., your signal is actually quite okay coming down, you're looking at sort of 10 5 centimeter levels of accuracy. If you have 2 megahertz worth of spectrum, well, you need 3,000 samples of that to then help you get a measurement. And this trade space really exists because, number one, you cannot always get the spectrum you want. And number two, that the number of measurements that you perhaps need to take will then tell you the time interval with which you can get something. So in 2 megahertz, if you were shooting off a pseudo-random noise code to get a measurement, and then you're detecting the phase, which gives you then a time of flight, and I need 3,000 of those packets come back, well, that tells me a minimum time. It tells me a minimum time then between my observations. And so you can start to play with the trade-off between these. So usually we use a Kramer-Rao lower bound trade space, which is about how we take an estimated value and then to determine then the variance that it might have. On the right hand side here, what you've got is essentially these same plots and these same curves, but now with the precision added to them. So it maybe is not so great, that you might pick, if you pick the best one, the 1 gigahertz signal, and you need to do that perhaps at Ka band or even higher, well then you can get then sort of error and precision that really does reduce very, very quickly when you've got a less noise-free signal. If you were to take the worst one, the 2 megahertz, and you needed 3,000 samples of that, yep, of course it does get better over time, but the variance doesn't. Okay, it's always going to have, that's 10 to the 1 there, it's always going to have, 200 meters worth of error on that measurement. Okay, so we have to kind of then play with this trade space and to understand the variance of our measurements. So how might we do this? Well, if you wanted to play around with different signals of different sizes, of different powers, well, then the way that you would do this is through radio systems. And one of the things that I look at a lot here are software-defined radios, which is where you can configure a radio system to do different frequencies. And so if you were measuring the range between 2 satellites that were slowly getting closer and closer and closer together, well, you might then want to use different frequencies to give you different levels of accuracy. Okay, this would allow us then to save power and to then build an instrument that actually everyone could fly. So on the left-hand side, we can see here the step between each of these functions based on the amount of bandwidth that you might get at each of these different channels. So you could get a lower bandwidth here, very tiny, and you can get a higher bandwidth at 5 gigahertz. So you can get them very precise. And this is a trade-off of power. What we have on the right-hand side is perhaps, for instance, the number of satellites that you could detect at any given instance. So if you had something working at 30 megahertz, which is a real sort of HF channel, then you can detect your local number of satellites around you, and you might be able to get anywhere from 50 to 100 satellites just to know what is in your local area. If you were to go then up in the band at VHF, well, then you're measuring at the 10 ones. And this is really the idea of you need to know locally what is happening around you. How many objects do you have around you? And do you need to take any actions? And so that's the sort of thing that we want to sort of build up as perhaps our instruments that we would perhaps want everyone to fly. So what are we doing here at Surrey? Well, I use my students to build electronics towards this sort of idea. And I've had a team of here that you can see there's about half a dozen sort of people, and I work closely with AMSAT UK as well. And we're building one such system that can do ranging transponding as well to and from low Earth orbit, or wherever someone will put this payload. So we've built a good half of this system to flight level already in our clean room, and we're just looking for then a place for it to go. So where and why might we then want to work with AMSAT? Well, this is the amount of data observations you might get, for instance, on a mission. I've been working closely with ESA on their OPSAT mission, and one of the things we looked at is plotting, where their data was being collected from for their ground stations. Now, as soon as you then, if it's ESA's owned ground stations, that's a certain number of observations you can get. But in these other areas, you maybe don't get observations. But working closely with them, with some organizations like the amateur radio enthusiasts, you can then start to fill in big parts of the map, okay, to know then of where you might get them. So it's about working internationally to get more data, more observations from more places around the world. Okay, so really that's what I wanted to talk to you today around my talk about sustainability, the fact that there are all these objects, that really observation is king, and that we have to make sure that we're then following and understanding the variance involved of when we take these measurements. So it might be great that you've got a telescope that's operating to and from the ground and they can look at things, but if the variance is 10 kilometers, is that useful? What do you need to do engineering wise, or who do you need to work with to make that better? We talked as well about object ages being from tracked versus perhaps untracked objects, and how many conjunctions that might look like in a day. And the fact that when we talk about observation, that we need data sharing and ethical policies that work for us to meet this demand. Okay, the issue that I have in one of my projects is to get conjunction data messages for a particular project. It took them about 6 to 9 months just to get all of the licensing information owned about the data. Okay, so it isn't just the fact that real measurements and observation is king, but data ownership and policies around data ownership need to be investigated as well. And lastly is that we're then using kind of all of this information to then kind of build a new ranging radio instrument that perhaps everyone could fly, to really promote local point-to-point sharing for conjunction arbitration, to prevent sort of the Kessler events and collisions that we're all so terrified of as well. And if you can, consider working with amateur radio and amateur frequencies for your teaching and learning, if you're exploring some of these areas, which is what I do. And with that, I'd like to say thank you. Would happily take any questions.
Thanks, Chris. I get a lot of information. You've packed into a small amount of time, so that was very interesting.
Yeah.
And I think, again, from the teaching point of view, two interesting things in terms of getting students to think about the issues around, what does a good observation look like and what risk does that leave you with? I think that's a nice approach there. And for those universities that have that option to actually do projects, physical hardware, software, then a good way again to engage in the topic, to build a payload or whatever that then links into that issue of how we're actually going to try and solve some of this problem. So,
or even just understanding your variance of when you're propagating an orbit, just know that, like, if you're propagating it and thinking in 24 hours, that's going to be plus minus a certain amount of range, which is perhaps not useful if you're looking at conjunction, because really what happens is you take these measurements and they get closer and closer and closer until you might be too late before you can make a decision. And so we have to then create point-to-point sharing systems, actually, like you have, with ships. In the ships we have that for AIS systems for tracking. We do the same thing for planes. We have ADS-B on the planes so that we know where they are, that is standardized across everywhere. And we need to do the same thing for space. The question is what could and should that look like, to make sure then that we don't ruin an environment which is not just for one company but for everyone that needs to operate there.